So, hello everyone, welcome back to the day 3 of week 2. So, today we will be practicing linear regression and logistic regression. But before we start, let's quickly go through the things which we learned in the last 2 days. So, what is linear regression? It's a way of finding a relationship between two variables. One is dependent variable and another one is independent variable. Independent variable x, our features are independent variable here because they don't depend on anything, and y, which is our target, depends on x, so they are dependent variable. And in linear regression, one of our goal is to find the best fit line which fits this data set best. And by best, I mean that the distance between any point and, and distance between any point on this data set to this line is minimum. Now, how we will find this best fit line using this equation. This is the foundation of many models in machine learning. Y hat equal to weights multiply x plus bias. Bias, W and B are parameters called weights and bias respectively. Now, W shows how much importance a feature holds, and B bias is like offset value, provides some flexibility. So what we need to do is to find the best fit line. We have to find the best value of weights and biases. And how we find this double how this value of and how we find the best value of W and B using the loss. This is the loss function, mean squared error, and what we do is we minimize this loss using the gradient descent, and after minimizing it we get the best values of W and B, which will give us the best fit line of this model of our model. And what is happens in gradient descent, we find the loss using the current W and B, then we find the gradient, which is just differentiation of each parameters with respect to loss, dW and dB, and update the parameters using this equation. Using these equation, W equal to W minus LR multiply dW. Then we will find the loss with the new parameters. We will find the loss with the new parameters, and we repeat this process, like we repeat this process entire process again and again until we will have the minimized loss. Minimal loss. When we will have minimal loss, we will have the have the optimal value of W and B, and that's it. After we have the most optimal value of W and B, we can put it in this equation and we will get the best fit line, and we can predict any values for this model. Now, multilinear regression is nothing but it has more than one feature. That's it. Everything else is same. Its equation looks like this: a new parameter for every feature, and plus base. That's it. It's everything is same like simple linear regression, but one difference is we have more gradients because we have more parameters. So for every parameter we have to find the gradient, and then we repeat the gradient descent process. And by the way, initially these weights and bias are initialized randomly, so we will initialize them randomly, and then we will update those using gradient descent. And last logistic regression. One difference between logistic regression and linear regression is logistic regression is used when our data set have discrete values, but linear regression is used when we have continuous values, and logistic is used for mainly for classification, binary or multiple class classification. So everything is in there are main difference between logistic and regression is the output of our equation let's say called z equal to w multiply x plus b. The output of our equation is passed through a sigmoid function, which will convert our outputs into the probabilities, and then those probabilities are passed through a loss function. Binary cross entropy loss function is used, something like this, and then we will repeat the steps of gradient descent. So what happens is we pass our output through sigmoid function, we get the probabilities, and then we pass it through binary cross entropy function, binary cross entropy loss, and then we repeat the steps of gradient descent. That's it. We find the gradient of dw and dv. Sorry, we find the gradient of each parameter, and then we will have the most optimal value of w and b when we have the minimal loss. Now, during prediction, what we do is we set a threshold. Let's say our threshold is 0.5. So, if our values, if we pass a value through our model and we get the output which is greater than 0.5, which is greater, so means greater than threshold, we will say that this value belong to class 1, class, and if less than 0.5, then we will say it belongs to class 0. Because logistic regression is used in classification. So let's say there are two classes, class 1, class 2, and you will understand things more deeply in coding during the coding part. So let's move to the coding section now. So now let's start the practice. First of all, linear regression, and I have already created this notebook. We'll implement the important parts, but to save time, I have already do some data pre-processing steps, but don't worry, I will explain them as we go through. So first of all, import all the libraries, and then we will load this dataset. I find this dataset on the internet, and you will also get this dataset, so don't worry about it for practice. And then let's see how this dataset looks. So in pandas.head will give the first 5 values of our dataset, first 5 rows of our dataset. So basically this dataset have one feature and one target, x and y, and then let's drop the missing rows which has some missing values using drop.na. So, and it is very important to drop or do something of those missing values, because they will create problems later during the training. And then let's see how this dataset looks like. Actually, this dataset looks like this. It's very actually clean dataset if you think about it, and perfect for linear regression basically, but in real world you will not get this kind of a dataset. And then let's convert our data, get the values for our data from the dataset in form of arrays. Basically dot values will give us array of all these values, and then we normalize our x train, y train, all these. Normalizing the data is very important, because scale invariance, to get the scale invariance, it's important. Suppose some feature have outlier value or very big value, so this will, if we have outliers or these kind of values which are very big, will affect the learning of our models. And so by normalizing, we will get a data which will have mean 0 and standard deviation 1, and the data will be scale invariant, means the scale will values of features will not vary that much. And so how we do it? What we will do is we find the mean and standard deviation, and then we subtract the mean from each data point, and then divide that by the standard deviation. So let's do this. And since we will be doing dot products, lot of dot products, so let's add one dimension to our data sets. Sorry, add one dimension to x train and y train. Now using expand this add one data set, axis minus 1 means at the end in the column, end of the column. So and let's see its shape now. See, there was its just have one column, sorry, rows only, and now it has this shape. Now here comes the important part. Compute the loss. We know we will be computing the MSC. So left before that, let's do this ln y, or you can do y predict also, but let's prefer this, and then return. What we will do is, let's return this np dot sum y predict minus y, and then we do the square. This is what we do. Okay, now, and sorry, I forget to actually, and before, let's remove this y. Let's do np dot square and divide it by n, so that we will get the mean, and then add a. Now let's time for our training. So first of all, lost history, which will keep the history of all the loss in, we will add this into the list, and then learning rate, learning rate equal to 0.0, let's say 0.1, and if pose, let's say 500, and let's create a fit function where our data model will be trained, and then initialize the weights and bias. So np dot random dot and changed our weights and bias should be small, so I am multiplying it by 0.01, and it should be 0 bias. And now let's create this for epo in range epos. So let's compute the gradient. Sorry, let's compute the predictions. So it should be equal to y predict equal to np dot x comma w, sorry, x comma w plus b, and then let's compute the gradients, and it should be np dot x, it should be equal to, and actually one more thing, let me just define n again, ln, it should be, and it should be equal to x, ln, sorry, y predict, and before to calculate the gradients, let's do, in the previous last 2 days notebooks, the gradients was like dot, and then np dot multiply y predict minus y, and so y minus y predicted should be y minus y. It can be y predict minus y, then this negative sign will not be there. And here let me fix this also, y minus y predict y, or let's say our prediction will go here, and np dot here, and x and divide by n, and our base gradient will be -2 multiply np dot sum y minus y predict slash n. All you have calculated in it was in the assignment, in the task 1 actually, if you know it. Now let's update the parameters. W equal to w minus learning rate multiply dw, b equal to b minus learning rate, right, dv, and compute the loss equal to, we have defined the already compute loss function, which will be equal to y minus y predict and loss history dot append. Wow, it's actually giving only. And next part is easy. So let's say if we pause divide by, it's actually very simple, and we want to return weights and biases, which will be optimal value finally. Since we are using 500 pose, so let's do this 550, and I hope everything is fine. And one more thing, yeah, I will be using I will be extracting the number of features from our dataset shape 1, and then let's do this. So because if I have one feature in the dataset, then w have only one value. If I have, let's say, 3 or 4 features, then number of features will be 4, because then this shape will be 699,4 or any other shape. Then we will get the exactly that much value, those values of w. So let's do this, and let's now see if it works or not. Output fit x train comma y train. Let's see, or loss. Okay, we are getting the, it's working. And let's actually make predictions on the test data. So let's say our predictions should be equal to np dot np dot, or I think you can actually create a function forward name, which will be forward, and then place it here, and you can call it over again for things. But let's say here goes, and we will be multiplying it by, since output 0, because output we have 2 w and b. It is, our function is returning weights, and output has 2 values, weights and bias. And let's see, and actually we can actually visualize this. plt dot scatter, let's visualize them. X test comma y test, how good our predictions are, and plt dot plot x test comma predictions color equal to red. See, this is a perfect line we get, and one of the reason is that this data set is ideal. You should practice on Kaggle. You can practice on Kaggle. There are some good data sets. And now let's see, and actually let's plot the loss now. But so do something like this, np dot range, or we can do range epoch, number of epoch, and then plt dot plot loss history, and let's say x plt dot x label equal to x label is epoch actually, and yeah, plt dot. So let's do this. Now you see our loss is not decreasing as much at this point, and basically what you can do is you can try some other data sets. You can change the value of pose and learning rate, and hope you get this part. It's very easy how it works. So, and now I think we have done everything. Only thing left is logistic regression. I actually created this also. So now let's start logistic regression. So now logistic regression, you will also get this data set. I actually find it on GitHub. So let's start. First read the data set. It's all are the same thing, and then we will actually, this data set is quite like, it has user ID, gender, age, estimated salary, and purchased, but we are only interested in these two. Purchased is our target and estimated salary is our feature. So we'll get our x and y. I am calling them x log, y log. So it means for logistic we are using them x log, y log, and nothing else. That's it. Turn them into features, and yeah, and let's see what kind of, it's actually, there are purchased have only two values, 0 or 1. It's binary classification, and we are trying to estimate salaries. So let's see. So if you even plot this, because y is only two values, 0 and 1, so this will look like something like this, and then we will normalize it. Let me write it here. Normalize the data set for the same region, scale, invariance, and then let's go and now define sigmoid loss, sigmoid return np dot 1 plus and exp. It's actually helpful. If you, now after that, let's define the loss, and let's call it bc, and what it will take y and y prediction, our prediction, and since we have two values, let's find them. Y1, no, I will know. Let's break it down. Y equal to y multiply by np dot log y pred, and then y2 will be equal to 1 minus y. You did it in the notebooks, in I think task 2 notebooks, so it's quite, you will already know it. Let me quickly go through it. For this data set, one thing, I will not be dividing it into test set and training set, but but you should do it because of time constraint. So now we have this, our data set, and then let's go for the now training phase, learning. Let's call it LR here. Let's keep it slightly big, and epoch, let's say 500, and note and features, we don't need it. So what we will need is cost function, cost function, and then let's define the function log fit x comma y, and then y predict will be equal to x multiply by w plus b, but we haven't initialized them yet. So let's initialize w equal to np dot random dot rand and multiply by 0.01 or b equal to 0, and let me cut it for let's for epoch in range epoch compute. Let's compute from the gradient w multiply by x plus b and y, then we will pass, as you all know, we will pass it through the sigmoid. I predict maybe dot mean y ped minus y. Actually, let me quickly see it if this is correct or not. So I think it's correct. I think it's correct. Let one thing, let's get it to ln x, yeah, x, and then do it 1 divided by n multiply by np dot sum, and it will be equal to, actually let's make it easy how we do it in the notebook. dz equal to y predict minus y, and then it will be easy now. Yes, x multiply dz and dv equal to 1 divided by n np dot sum w minus lr multiply by, we will update the parameters, time to update them, lr multiply db, and then let the loss equal to bce, but we will take it as y predict and cost dot append loss, print if pose to we want to print that now we have taken 500, so let's say 50 equal to 0, so print low epoch equal to epoch and loss, yeah, loss equal to this. Now let's quickly run it out, equal to log fit x log y log y log. Hope it works. Yeah, it works actually. And if you think about it, here is interesting, very interesting thing will happen. So if I plot it, plt dot plot, and it will be, wait a sec, plt dot plot cost with respect to epoch, let's say iter, let's call it iter, or np dot range epoch, and this iter comma cost, plt dot x label equal to iterations, plt dot y label equal to cost loss. Now if you print it, then what you you see this, we hit the plateau. Now if you, in this data set particularly, if you increase the number of epochs or trying to change the learning rate, this loss will not change. So it, what does it mean is the data we have is insufficient. But anyways, this is for the hands-on give, we want to give you an experience. So, and it's these things like this will happen when you will hit the plateau. So now let's define a prediction function, which I told you about. So let's do this prediction quickly. See, note prediction, we will set a threshold here, not some random thing. We'll set threshold here. So let's say threshold equal to 0.55. probability is, value of sigmoid is 0.5. then it belongs to class 1, then means the buyer will purchase it, and if it is less than 5, so it will be 0 and the buyer will not purchase it. Y print class equal to 1. okay, so if greater than threshold, then it will be 1, and less than threshold, then it will be 0. So let's define predict. Sorry, predict x log actually. Yeah, and w equal, instead w will say out comma 0, out comma 1, and let's see. Okay, sorry, actually it doesn't, made a mistake. So it's working now. Let's see. If you see, we'll add 0 1 0 1 0 1 everywhere else, like, oh, okay. So now, and actually to get a good output, let's np dot array, you will have a nice look. Yeah, you see, this is the prediction function. So that's it. Hope you like it.